The atomic hypothesis. We spent the first part of the course thinking about the fundamental underlying principles of the physics. We looked at kinematics, Newton's laws, in particular F equal ma, the principle of the conservation of the momentum and conservation of energy. Then, armed with that groundwork, we started looking at particular forces. We've looked at gravity, we've looked at electricity and magnetism, and then we recognized that electricity and magnetism were unified. Maxwell helped us to visualize this unification and think about electricity and magnetism as a flip side of the one fundamental true force of nature. We discovered that force of nature tells us about light and light waves, which led us to think about waves as a general feature of the world. That spread of the idea covers a good chunk of the classical physics. There is one key important final story which will lead off to many different consequences. It is perhaps one of the greatest ideas of all of the physics, and I have been alluding to it all along. It's a part of our culture, and everybody knows that the world is made of atoms. Nobody knew that. Even 100 years ago, people were arguing about it, and 300 years ago, people had no idea about how you would demonstrate whether the world was made of atoms or not, right? Today, I want to talk about the idea of atoms. How we could convince ourselves that the world is made of atoms during the period of the classical physics, from Newton all the way until the contemporary times. Let's go back a little bit to first and think about Greek philosophers. People have always been wondering about what the world is made of. What are the building blocks? It's a very natural question. 400 years BCE, Democritus had some writings in which he postulated that the world is made of the fundamental little uncuttable objects. It's the bottom of the line, and uncuttable in Greek is atomos. That's the origin of the idea of the atoms. Aristotle looked at these ideas and said, "No, I don't think so." Remember, Aristotle believed in the qualities, and he believed that the qualities are not divisible, so it's not dividable, right? So divisible into chunks, and so he had a world view that the world can be divided and subdivided indefinitely. So there is no border, right? In that era, it was a philosophical debate. People couldn't really think about the measurable consequences of the one idea versus the others to test so that you could disprove one and begin to convince yourself of the others. Right. Let's think about a picture of this. If I give you a stick of the butter is a material and has a certain defining characteristics. Aristotle would be perfectly happy to start listing them. It's a yellowish and it melts at room temperature. It has a certain density. Density is a mass per unit volume. That's not quite how heavy it is. It's how heavy it is for a given amount. And if I chop the butter in half and now I just investigate half a stick of the butter, it's still clearly butter. I haven't changed the character of the material, I have less of it, but it's still yellow and it still melts at the same temperature. It still has the same mass per volume. I have a half as much mass, but I also have a half the volume. You can now start chopping it in half and in half. Now you have a patient. Now you have a fraction of the pot, but it's still butter. What Democritus argued was it's not the butter all the way. There is one final cut, and he didn't know where it was at what point or how big that last piece it was. He assumes that it was extremely tiny, but not infinitely tiny, and that's the last piece of the butter. If you try cutting that, You can't. If you did, you wouldn't have butter anymore. Whereas Aristotle argued, it's a butter all the way. You could just keep dividing it in half and in half as many times as you like. It depends on the sharpness of your knife. It's so philosophical, not practical. How are we going to decide this question? Well, the nature of the science, classical physics, is to think about consequences. If you believe that the world is made of the atoms, what measurable consequence can you think up? And we'll go test those. Wow. So the hypothesis thinking だね。Yeah. We are trying to create a world view that's as simple as possible. That's one compelling argument for why you might believe in atoms. That is because it's a nice simple point of view, but it has to go beyond that and we have to be able to test them. People spend an entire lifetime trying to think about the consequences of the atomic hypothesis, and I'd like to sketch out some of the big ideas. Nowadays, we can imagine atoms not with our eyeballs, but with devices like scanning electron microscopes. We can see individual atoms by their evidence left behind on the computer screen. So we certainly have a very direct evidence today that atoms exist. They are real, but even back in the 1700s, there were already some pretty good clues. People were beginning to develop the idea and becoming more and more convinced that it seems like a useful and ultimately correct description of nature. Wow. It turns out that the atom is a lovely topic in the classical physics. I think atoms belong squarely in the field of the classical physics, and yet they also form a bridge to modern ideas. Because classical physicists want to know what the world is made of. We've been pretending that the world is made of point-like objects, and now we are talking about what those point-like objects are. Today we ask what the atoms themselves are made of. You can keep on digging deeper and deeper, and I would argue that the classical story ends with the atom. The atom is the bottom line. It's a simple, uncuttable, fundamental building block, and so that's where we are going to zoom in for this lecture. Thank you. If you don't believe in atoms or you don't know about atoms, much of the classical physics still continue to work. You can talk about Newton's laws for a moon or for a baseball, and we can pretend that the baseball is a point-like object, or that moon, for that matter, is a point-like object. That works just fine. We've talked about this throughout the course, that we can simplify our thinking, but now we are asking, well, are there true point-like objects? Is this a physical reality? If there are, then our philosophical vantage point that the world is ultimately simple, our idea of reductionism, that complex things can be broken down ultimately into their building blocks, and the determinism that if you know the building blocks and you know the Newton's laws and conservation laws, you can build up to arbitrarily complex system. All of this leads us to believe that the idea of the atoms could be very fruitful. Wow! Ha ha ha, he. Let me be a little bit more articulate about what the atomic hypothesis says. The world is made of atoms. Every material object, solids, liquids, gaseous, all objects are made of their fundamental atoms. There are different kinds of atoms. For instance, carbon is one kind of atom, nitrogen is another, oxygen is another, and hydrogen yet another. There are all atoms that are present in our bodies. Those 4 kinds of atoms describe a good chunk of your body. And if you add a few more, they describe a good chunk of the physical world. All you are doing is combining them in different ways. That is chemistry, yes! Chemical reaction. In the end, it turns out that we need about 100 of these things to describe everything we ever observed. Just a few more than the 100 fundamental atoms. And every atom, of course, can be repeated, so you can have many different carbon atoms. But they are all identical. They are all identical, absolutely indistinguishable from one another, and that's what the world is built of. Whoa, really? The periodic table, the graph of the elements that is always up on the blackboard or above the blackboard in the chemistry and physics classes, is a list of all of the known atoms. Hydrogen is in the upper left-hand corner, and then helium working its way down through the periodic table, listing all of these hundreds. If you know them and you understand their properties, you understand what they are made of. All you really need to understand is that they have a mass and they have a certain interactions with one another. Then you can build anything else. What is butter? Butter is made of molecules which are built out of the carbon, nitrogen, oxygen, and hydrogen. The idea of atom is going to help us. It's going to help us to make sense of the physics and chemistry and many other branches of physics and chemistry in particular. Yes. At the beginning of this course, I was a little bit dismissive of the chemistry. I argue that it is derived from physics, and so physics is a fundamental. Chemists, of course, would bristle at that thought, and I have to give credit where the credit is due. The idea of atoms really arose from chemistry. Chemistry and physics at one point back in the 1700s were intimately connected. They were investigations into the world, the natural world we live in, and the way they were investigating it evolved until nowadays. People who mixed chemicals and look at their reactions are doing chemistry. We don't call that physics anymore, but it's really still is trying to understand the building blocks of the world in many respects. Sure. Now, back in the Newton's era, there was no chemistry. Of course, there was no physics either. He invented it, but Newton spent time doing what we now would call the beginning of the physics. He also spent at least as much time, maybe more, doing what we call alchemy. Now, it has a chemy in it, and it sounds as if it is related to the chemistry. It's kind of a proto-chemistry. It's a mix of mysticism, superstition, and the quasi-religious cult approach to understanding the world. Nowadays, at least as far as I know, there is nobody seriously pursuing alchemy, but in Newton's era, doing alchemy meant what you think of as classical chemistry experiment, mixing the things, heating them up and grinding different materials and trying to figure out what's going on. Except that alchemists were not behaving like a scientist in the contemporary sense, right? So, in particular, the culture Newton was helping to create in physics that was so enormously valuable is what it meant to be a physicist. Yes. Sure. So let me say it again. So in the particular, the culture Newton was helping to create in the physics that was so enormously valuable is what it meant to be a physicist, to do experiments, to try to hypothesize about underlying physical explanation, to then publish this work, to go to the meeting to talk to other knowledgeable but skeptical scientists who are interested, who can themselves repeat your experiments and figure out where you are right and where you are wrong and come up with alternative or improved hypotheses. That whole culture of science didn't surround alchemy. Alchemy was done by yourself, and you would write up your result in the little cryptic codes so that other people couldn't steal what you did. This is anti-scientific, right? It was by and large recipes. Wow, it wasn't a fundamental principle-based scientific study. Because of that, Isaac Newton, although he spent an enormous amount of the time doing alchemy and he wrote quite a bit about his alchemy, very little of his work followed through or contributed to our contemporary scientific development. It's too bad, but if he had treated alchemy in the same way that he had treated optics, mechanics, or astronomy, it's quite possible we would have progressed more rapidly in the chemistry field. Meaning, we are pretty much behind our original plan because of the secrecy of the Isaac Newton. Wow. Still, we are taking advantage of his knowledge in the physical field, right? I want to talk about how we started developing the atomic model by following two paths. And one of the paths was with chemists. The other path was with a physicist. I'd like to start with some chemists and think about the early progression so that we can understand why you might have believed in this crazy idea back in an era when there was no hope at the time of the being be able to see individuals' atoms. Wow.